Welcome everybody. We're going to continue our lecture on Markov Chains, Metropolis-Hastings, all of that. There's a lot to talk about. Lots of theory as to why these algorithms work. Just remind you, Markov process only depends on the past. We've seen Markov chain Monte Carlo at play. We haven't seen the Metropolis-Hastings algorithm, and I'm going to claim Metropolis-Hastings, i.e. it's okay to call it Metropolis, is MCMC. So Martin was like, I don't know what this Metropolis-Hastings thing or MCMC thing is, but I remember reading #1 algorithm, Metropolis, same thing. So, Hastings deserves a touch of credit. I'm going to ask this question later. Who deserves the Nobel Prize if there was such to be given? I think this is a tremendous achievement. Allows us to do a whole bunch of problems. MCMC, Markov Chain Monte Carlo, and I'll just point out, this is capitalized always. This is capitalized always. And this is capitalized always. In this one, you have a choice of whether or not you want to capitalize it. So you can write things like MCMC or MCMC. If you're doing a full initialism, if you're using an initialism, it's different from acronym. So, does anybody know the difference? An acronym versus an initialism. A lot of people like to say that's an acronym. Hey, they're close enough. I mean, we can nitpick over what we say things are, but technically this is an initialism. So something like FEI is an initialism. But if we said FIBI, that's an acronym. So it doesn't matter. Small tidbit points. This is not capitalized because it's not the name of anything. So Monte Carlo is a place. We discussed it earlier. So does anybody know what Monte Carlo is? Monaco. So coast of Monaco, this small sliver of land between Italy and France. So you're in and out pretty quickly. There's an F1 track there. They do a lot of gambling. So that idea of random process, gambling, I guess casinos are a big Monte Carlo factory. And on average, they win. So you take your money, but you have a fun trip. So you're paying for the variability. Variability is the most important thing in a casino. The most important thing in a random process. Without variability, you just walk in and it's like, hey, you owe us $5 million. That wasn't very fun. So you gotta lose it slow. Random process, Monte Carlo, Markov is a person. So mathematician. Anyway, Markov chain Monte Carlo processes, let's just say I have a couple variables, x1 and x2, for processes that step around space in a Markov fashion. So I'll say this is our first step, we'll call it state 1, right here. Our second step, state 2, it moves to, so it transitions from here to here, to here, to here, to here, to here, to here. And eventually, a process will converge to something. So it might walk around this area right here. So what Markov chain Monte Carlo is for is to sample from distributions. And we run them in a limiting format until they achieve the stationary distribution. Eventually, I'll say, they sample from a target distribution. If you've ever taken a stochastics class and learned about Markov chains, what they usually do is they give you the Markov transition probabilities and say, work out what the stationary distribution is. So, if you haven't had that pleasure, that's what those classes do. In my class, we're going to flip this on its head. And I already know my stationary distribution, so I'm going to form transitions in such a way that eventually it samples from a stationary distribution that I set out to sample from. And in our case, that stationary distribution is going to be the posterior distribution. So Bayesians, we're constructing probability distributions on unknown things. We want to sample from it so we can learn what the shape of that curve is, where it places mass. So again, stochastics process class gives you the transition probabilities. You work out the stationary distribution. My class, I've got the stationary distribution and I work out transitions so that it stations itself at the posterior mass, where the actual target is. The eventually thing is just saying that the samples, the frequency of samples, ends up laying in the probability mass proportional to how much mass is actually there. So in a sampling scheme, the whole idea is that the frequency of the samples represents the probability of being there in the first place. So these algorithms do that. They're not just random. They're convergent to something. Let me write down what the algorithm is. So this is what my code does. Look at it more intensely. But here's the Metropolis-Hastings algorithm. First, I need to tell you something about proposal distributions. So the idea is that I don't know how to sample from my target. I'm going to write down my target as this. So our target is the posterior distribution. We usually write it like this. So what is it? It's proportional to likelihood times prior. And the beauty of this algorithm, and I'll tell you why soon enough, is that you don't need to figure out what the normalizing constant is. If you needed to do that, you need to integrate over the space. If I can integrate over the space, I can sample from it. That's the hardest thing I can do, is integrate over the space. If I can integrate over the space, I can estimate where mass is, so I know where samples should be. Here's the cat's out of the bag. We don't like to integrate. That slows us. It's hard to do. It's the calculation we always need to do. It's the hard thing to do. And a lot of times there aren't analytical forms. So it's like, you've got a couple techniques that you can use. You can approximate whatever it is you're trying to sample from so that you can integrate over it. So quadrature will do things like that. Or you can sample from the distribution such that the frequencies of samples represents the probability mass in an area. Those are kind of the two things going. It turns out the Monte Carlo procedure, sampling procedure, is better in high dimensions. Dimensions over 3. So there's a big breakdown of quadrature techniques that these don't suffer from. Maybe we'll go into that detail later. So basically, the stuff works. Under 3 dimensions, you can be deep in terms of how many computations you need to do to get an answer within some precision. Go over 3 dimensions, and all of a sudden this stuff works really good. This used to be a big deal, because getting a lot of samples was hard, but nowadays it's pretty easy. So we'll talk about all these details as we go. So here's my target. I'm just going to write it down like this. But it could be anything. Some distribution, I know it up to proportionality. I know what the shape of the curve is. In our context, it's a posterior. But this algorithm could be applied by anybody that wants to sample something. So I usually say to the asymptotic frequentist, forget about all that stuff. Just work out what the probability is of this thing. You got your null distribution. Tell me what the exact tail probability is. Don't approximate it with a chi-squared, because you're not there yet. So everybody could use these tools. So it's a cultural thing that only Bayesians seem to use MCMC. A lot of people would benefit from the choose. So here's an idea. You can't sample from this. You don't know how to do it. Now, if the distribution was something like a gamma or a normal, you know how to do it, at least in spirit. There's a package out there that helps you to do it. If you've taken Monte Carlo classes, you might be able to construct one of those functions. Box-Mueller for normals. Gammas, there's a similar formula that people can use. Transforming uniforms to other things. But we can't always do that. So don't always know how to sample from a distribution. So somebody just give me like a sampling technique that you know about. Some algorithm for general purpose sampling. Jess, you want to take a shot? No clue how to sample from anything. So if I gave you a function and I said it's probability function, sample from it, not even a tool in the toolbox. EM, okay, so EM optimizes. So it maximizes something. It marginalizes and then it maximizes. So it's something that's used for parameter estimation, but it's no sampling algorithm. Now you can do Monte Carlo within EM, but that's different. So that's not sampling algorithm. It's a maximizing algorithm, it's a parameter fit algorithm in the presence of missing data that you marginalize over. Sierra, give me an algorithm.
To sample from the target?
To sample from any target besides Metropolis-Hastings.
Do I know the prior and do I know like
You just know a function. Give me a sampling algorithm.
I would sample theta and then plug theta in and sample from that.
That's not an algorithm. Let's try again. Lawsuit. Sue.
Yeah.
Which one? I'm astonished. It's okay. We'll have to be. L1. Don't know how to sample from anything. I give you a function, I say sample from it. Alex.
You want to produce data?
Just want to, I've got a distribution, a function I want to sample from it.
You use the uniform distribution to produce data and put the data into a function.
Okay, I do know an algorithm that's like that. So I'm going to interpret that as inverse CDF.
What?
Inverse CDF, is that what you're saying?
I don't know what is inverse CDF.
Okay. So, in my inference class, a whole bunch of you took chapter 5, sampling methods. So Cassell inverter, they go into it. Inverse CDF, they give you can't do that if you can't invert the CDF. Accept reject is an algorithm that a lot of people use. So you build a proposal, it covers something, envelope sampling. So how does that work in practice? Let me show you an illustration. Probably done this in kindergarten. So say I want to estimate, let's say maybe the area of that. So I want to know how much area is inside of it. Make the boundary look a little bit bigger so you can see it on the camera. So imagine that's just a thick line. I want to estimate it. Don't know how to do it. Yeah, that's right. So that's an algorithm. So Monte Carlo is a class of algorithms. It gives you a random answer in a fixed amount of time. If I wanted to do this, what I could do is I could imagine, I don't know how to compute the area of that, but I certainly know the area of the piece of paper because I went to kindergarten. So like kind of quick. If I could uniformly sample from the paper, there's a stripe inside. And I do this over and over again. Outside. What I can do is repeat that process. I don't want to destroy my head. That's what usually happens. So I would have a number of random points all over the piece of paper. So I'm imagining that I uniformly sampled on the piece of paper. What I could do is I could take a fraction of points that land up in here and multiply it by the area of the piece of paper. If you've never done that, you're missing out. So I multiply, let's say the area of this paper is like 3. You know, something times something, it's equal to 3. I take the fractional percentage of points right here and multiply that into 3, and it tells me the area of this. That's an algorithm, that's envelope sampling, set reject sampling. What's that?
I don't understand how this is done. You only count out the area of a certain data.
So, okay, so if I wanted to uniformly sample from the circle, now I have a uniform collection of points that are sampled from this circle as well. So I discard all the ones that are outside of it. So that would be my sample, and then I can use my sample to do the estimation. So yeah, there's an intermediate step in there. But say you wanted to estimate the area by sampling from this, and I don't know how to do it, I can sample from something that covers it, and then take the fractional subset. If this was a normal distribution over this, I could say I've got some sort of normal density, and I'm interested in a region right here. How would I sample from that? Probably sample from whole normal distribution and just take the points that are inside of this shape. Set reject. There's importance sampling. If you've never heard of any of these things, you've got to get on. This is the stuff that will make it so you can solve your problems. So, I'm not always interested in solving my problems fast. I've got to just get a solution first. So I need general purpose samplers. Except reject, there's a mathematical calculation you need to do. I need to measure the max height on my proposal distribution, that being the sheet of paper, compared to the max height of my constrained region. Always a mathematical calculation you need to do. Inverse CDF fails sometimes because you can't compute the CDF or you can't compute the inverse of it, even though they all exist. So I feel a little bit bad because I'm going to start you out with the best one, but people know how to sample, I'm sure. If you didn't, I need to reload all of your inference class. So you need to take that away. So come up to me with your report card and I'm going to scratch it off. You got to retake my class. So, okay. We're going to do a lot of sampling in this class. So if this is new to you, congratulations. So this is going to be fantastic. I want to sample from this thing. I need a proposal. So I've got my target. And I need a proposal distribution. And I'm going to give this a name. I'm just going to call it G theta. Some proposal. It's a distribution on theta. The only property I need for this proposal is these thetas right here need to cover this space. They need to live in the same space. So I'm going to say proposal, the only necessary condition that you absolutely need, although I would like this thing to have finite variance for obvious reasons. Otherwise, the sampler is not going to work very well if you have chaos. So saying that, it can still work. Proposal distribution, I'll say this is going to live in omega g. So I'll say theta is an element of omega g. And I'm going to say these thetas are an element of omega pi. Just because I'm not very creative with my notation. So these thetas live in a space, these thetas live in a space. So we need that omega pi needs to live inside of this. We need the proposal to be bigger than the thing I'm trying to sample from. So if I never propose values, I won't know whether to accept. I won't have any chance of accepting them over in the region, and I'll miss the space. So here's the algorithm. We'll get into some definitions in a moment. This is my favorite stuff. So it's how statistics works. If you understand Monte Carlo, you understand stats. It's just being performed on a computer. So pretty cool. Metropolis-Hastings. And this thing right here is MCMC. There are little embedded algorithms in MCMC that people say, well, that's not MCMC, or all MCMC algorithms are this algorithm I'm about to show you. There might be other things that people do to change the goal, but all MCMC is Metropolis-Hastings. And all we're going to do is argue over the proposal distribution. So the idea is I don't know how to sample from pi, but I know how to sample from G, and G is bigger. So it covers at least the space pi does. I don't need to do any upfront math in this algorithm, and that's what makes it popular. So there are a lot of algorithms that you have to do some upfront math and check stuff, tail domination, blah, blah, blah. The algorithm has 2 steps. So step 1, yeah, I did fill that in. Step 1 is I'm going to propose from G. So I've got some distribution, G, and I sample from under it. I know how to take these samples. What I mean by sampling is that in some area, whatever the area is under the curve, I get a frequency of samples proportional to that. So that's what sampling is. If you don't understand it, you didn't understand anything in stats. So that's the whole premise. These are variable under the sample. What are the sample? What are the properties of the sample? So I haven't told you too much about this distribution. It's pretty flexible. So, and I'm going to butter this distribution up in a couple of minutes. Step 2 is I decide whether or not I want to move to that proposed location. So step 2 is the Metropolis-Hastings acceptance decision. So a lot of times I'll call this the Metropolis-Hastings decision rule. The rule looks like this. I'm going to compute an acceptance probability This is the whole magical step. This is going to be the minimum between 1 and something I can compute. So this to me, very awesome thing. This thing in the denominator that I just scribbled out 3 times, this is what the denominator looks like. I have not introduced this notation yet. Let me finish writing this out and I'll tell you what it all means. So this is going to be G theta star G theta T minus 1. Just to be clear, this is the ratio of targets. This is a target ratio. And this is a ratio of the proposals. You'll notice that I'm evaluating them using the reciprocal form over here. So my theta star is right here. My theta T minus 1 is in the bottom. Theta star is in the bottom here, so they're flipped upside down. So So I usually call this the inverse proposal ratio. Okay. Now I haven't told you about a critical step. This is an iterative algorithm, as we've kind of explained, and you have to start somewhere. So there is a 0th step, and this is to initialize. So I'm going to start this thing out at theta 0. Then what I'm going to do is I'm going to run these 2 steps for a very long time. I should probably finish telling you what I do once I compute this probability. So once I have this probability, I flip a coin and I decide to do one of 2 things. This step concludes like this. I update theta. Theta t is going to be either theta star or theta t minus 1. So there's no rejection here. You either move to the new location or you stay where you are. And you recycle that sample. So I've seen this happen a lot of times with first year MCMCers, is they throw that coin away. Do not do that. This is not an accept reject algorithm. You keep everything. We'll keep talking about this. This happens with probability alpha, which is this number. And this happens with probability 1 minus alpha. So this is just a coin flip. So here's the algorithm. I propose, and then I make a decision. Stay in the same location or move. I want you to think about this ratio a little bit. Write it down one more time. So the MH decision rule you can think about it in terms of this probability. Pi theta star pi theta t minus 1 times g theta star g theta t minus 1. That's the same thing we wrote down before. I want you to notice that this thing right here, I don't need our normalizing constants. I can write in there likelihood times prior. The normalizing constant would be the same in the numerator and the denominator. Just write that down and be really clear about this. So this is likelihood theta star given x, pi theta star, and I have my integration. Likelihood theta, don't plug anything in right there. Pi theta, d theta. And I integrate over all of theta. Divide by likelihood theta t minus 1 given x, pi theta t minus 1. And if I wanted to be very inefficient in my time, I would write these integrals in there. Integration over the same space, e theta. Magic. I don't like wasting my time in computing things I don't need to compute, which make the calculation hard in the first place. If I could do that integration, I could do anything I wanted. Keep in mind, this is an integral over the whole space. Sometimes it's easier to integrate over the whole space than it is just a sliver of it. So, anyway, we never have to do it. This is the whole point of MCMC is we don't have to compute our integrals. So, you can write likelihood times prior up here. I want you to think about what this is right here. So if I have my target distribution, let's imagine I can visualize it. So we'll just do this in 1B, something weird. This is supposed to convey it's complicated and I don't know how to sample from it. But I want to point out, I can compute the height of this function relatively. That is, I can evaluate this. So I don't know what the confusion is, but every year I teach this. And people go, you said you can't sample from it, but you can evaluate it? Yeah. One is way easier to do than the other one. So I give you like the normal Gaussian function. You can evaluate it. Plug an X in there. Get whatever its number is. Sampling from it is harder. So grabbing draws under the curve so that the frequency of draws is proportional to the probability mass is a harder thing to do. So we can evaluate our function. There are schemes where some people don't know how to do the evaluation of the function. So in computer models, it's often like this. There's something called approximate Bayes computation. And so it's a method so you can't evaluate that. My class is always going to assume everything's parametric and you can evaluate it. So premise for the class. We always need to do that. If you can't do it, come and see me and I'll give you an algorithm. So I've read my Monte Carlo books quite thoroughly. I probably know the algorithm. So this is the ratio of these targets right here. And so let's say I was here at my previous time step. And then I propose to move here. That one's here. And this one's a little bit higher. So in the decision rule, it says, if this is greater than 1, you should probably make that move. Go ahead, make it. But be careful. Because you want to make sure you're welcome back. And that's what this other part of the ratio says. So if this is high, that's increasing the probability. This part of the ratio is making sure you're welcome back. So what's the probability, or in my case a density, this could be probability mass functions, densities work too. But if this right here, if it's easy to go back, that is this density right here is higher than that one, then make that move. So if this is greater than 1, you want to make the move. And if that's greater than 1, it says you're welcome back. Go ahead and make that move. So you're going somewhere better. And if that's greater than 1, you're welcome back. That's a good thing. So let me give you a life example. So I always want to do other things with my life. I'm not just coming to Virginia Tech every day, teaching, working on research papers. Amazingly, I have other stuff that I like. And I think about going off and doing it sometimes. So I could walk into my boss, Dave Higdon, and say, hey, I want to be a motorcycle racer. And I'm going to take the next year off. And he would say, that's great for you. I'll never see you again. So, because when I come back and I say, you know, this motorcycle thing, it was really cool. I was having a lot more fun in my life. This ratio is greater than 1. So it improved where I'm moving to in life. But then I say, it doesn't pay too well, and I broke my leg and my wrist this year because that's what happens. So people get beat up. We've got a couple of years that they can survive in this sport. And I come back to Dave and I say, can I have my professorship back? He says, no way. So you have to be careful. So when I think about Metropolis-Hastings, it's saying, try to move somewhere better, higher part of the space, but make sure you can move backwards too. This is a life lesson to me. So in our life, we need to explore spaces, check out different possibilities. And it says to walk around that space and compare things to each other. But make sure every time you make a move, you can come back. So Monte Carlo algorithms or sampling algorithms in general teach us about how we should live our life. We need to explore. We want to stay around high math stuff, but we want to check out the chaos every once in a while. So we have something comparative, and the way we propose in our life, you need to make sure when you make your moves, you can come back. If you never are able to come back, it's hard to explore the space. Martin?
Thinking about that second term, is it like to prevent it from becoming a greedy algorithm that just goes into something and then crashes?
Yeah, so it doesn't do that.
Or what?
No, it doesn't just hone in right here. So what this says, imagine this were 1 right here. Let's imagine that this thing was greater than 1. Let's just say I had an algorithm that set that up so that this thing is 1. We'll show you how to do that in a moment. That's called the Metropolis algorithm. The Hastings variant has this second term. We'll distinguish those in a moment. If this is greater than 1, then the minimum between 1 and something greater than 1 is 1. So the probability I make that move is 1. So if I see something better, go there. But let's imagine this ratio is 0.3. So this is only 30% as tall as that. It doesn't say don't move there. It says go there with probability 0.3. So it does not just trap you and move into like a maximum. There's always a probability you can jump away from it. So I'm not sure about the term greedy in that specification, but at least that tells you it doesn't converge to a point. What this actually does is if G covers the whole space that pi lives in, is eventually you start to obtain samples from your target. So let's imagine we started way down here. Let's say this was like theta 0. What would happen is if you kept recycling this, I propose from G, I can sample from that thing, it's easier. So maybe G looks like this. So G lives in the same space. I'm able to sample from this smooth thing. Maybe that's a normal distribution, something I know how to sample from. So what you're going to do is I'm going to sample from G. It's going to move me somewhere around here. But eventually, I'm going to start walking up this thing and obtaining samples from this region. But this stuff over here is junk. It's our burner. So from our lecture last time, that's what we're observing in this algorithm. So what it's doing is it's eventually reaching stationarity. Now I have to give you a proof to show you that this is true right here. So let me just make sure you understand what I'm saying is true. So fact. Eventually, this is an important word. The Metropolis-Hastings algorithm samples from pi, or target, whatever that target was. I'm just contextualizing it as a Bayesian. And the key point to write down the posterior right here is in the algorithm. You don't actually need to normalize it. So if you did that, you wasted a whole bunch of time. So that's kind of cool. So the samples eventually come from the right thing. I want you to notice that this algorithm is Markovian. So what do I mean by that? Exactly. Markovian. So the future sample only depends on the last sample. Needs to be bigger. So the space that it lives in, obviously it can't be smaller. So if G had a smaller space than it lived in, I could only learn about samples in that smaller part of the space. I'd never learn anything about the other part of the space. It just needs to be bigger. Now, I'll point out something like, imagine I'm trying to sample from a positive distribution, like a gamma. It only covers positive stuff. I can propose negative stuff if I'd like to. So I'm just going to always stay at the same location. I'm throwing something out that's no good to me. So if you looked at the ratio right here, this would be a 0 right here, and you wouldn't ever move. So the probability of moving would be 0. This thing would be a 0 if I threw something, a proposal, into a part of the space that it didn't have mass. So you need that indicator function in there to say there's no mass over there. So like in a gamma distribution, you might throw the negative thing into the formula, and it's going to foul up your function. What you need is something indicating that's a 0, you can't make that move. So if you throw something out that's not possible, you just stay there. Your Markov chain's kind of stuck for a while. So, and then eventually you throw something out that's maybe possible, and it takes its chance to move, and maybe it moves. So yeah, it's got to be bigger. Some people will tell you that the tails, this distance between these two functions, g and f, or g and pi, right here, is that that's not allowed to explode, get bigger and bigger and bigger. You'll notice I can reformulate this rule in terms of a pi over g and a pi over g in the denominator. So let me just write that down. I sometimes like to look at this rule like this. Pi theta star given x over g theta star times pi, I'm going to write it like this, pi theta t minus 1 given x g theta t minus 1 given x divided. So those are the same things. This right here is called an importance ratio. If you know anything about importance sampling, this ratio comes up. If you know anything about accept reject sampling, you compute that ratio at every step. And in Monte Carlo, Metropolis-Hastings, what I mean, you compute those ratios as well. So it turns out everything is corrected through the importance ratio, this ratio thing that we're doing. You think back to my example, that's gleaning in there. If this thing right here gets really big, and it can go infinitely big, you can have trouble. It'll slow down your algorithm. In accept reject, it won't work. It actually fails. You break an assumption. In importance sampling, it really spots you down. Some people would say your sampler does not work at all in those cases, but it turns out it's just really slow to work. But in something like accept reject, it doesn't work. You actually get the wrong thing. These ratios should be nicely governed. What that means is that the tails of G are vanishingly thin compared to where pi is. What it really means is that you never learn about the tails of pi. It takes you a long time to learn about it. It just slows down your sampler. Okay. I need to prove to you that this is true and this works, that this does actually sample from pi eventually. I'm not prepared to do that proof right now. Definitely can't do it in 5 minutes. Saying that at 2 a.m. if you woke me up, I know how to do this proof. We'll get to it. So I think this will be the first edition of this class that we actually prove this works instead of just giving it to you. This is the Bayesian savior right here. This is the whole thing. So the whole state of the field of Bayesianity became, what's a good proposal distribution so this samples quickly? And so Bayesians in the late 90s, that is what they did. In the early 2000s, that's all we did, pretty much. They work on applications too. The field's kind of evolved from there, and I wouldn't say it's the super in vogue thing to do right now. It's just figuring out G's, but I still like to do it. I still think it's useful, and I still like papers on it. So, but all of MCMC is a discussion about that. So how do you pick good G's? I'll show you what I did in my code. I'll give you some handouts so you can finish your homework. But this is a good G. So this is sometimes what people like to use. This is probably your most popular G. Doesn't always work. I'm imagining theta is one-dimensional in this example. Normal example. That's a normal distribution that's centered in my previous time step, and it has variance psi squared. What's really cool about this, and you can check it, these are symmetric in these arguments. Where I'm moving from and where I'm moving to. So this is a symmetric function. That's 1 in those cases. This is called a local Brownian random walk. And the whole name of the game is to pick psi. If you pick psi too small, you barely move. It'll take a long time to sample. If you pick psi too big, you might be jumping out from the posterior mass too quickly. So I need to talk to you more about that. In the meantime, I'm still behind on giving you an actual Markov chain lecture, and we need to do that. So I'm sure a lot of this is pretty mixed up in your mind, but let me just show you a few things real quick in the last minute or two. Consider a Markov transition matrix looking like this. Right here. So this is the S state. This is going to be the number of states. So this is the S state transition matrix. So it tells me the probabilities of moving from one state to the next. In our example, that's a continuous space, and I cannot write it down as a matrix. So I'm using this as an idea, but everything is extendable to the continuous class. So these probabilities are the transition probabilities. So this is the transition probability of moving from state I to state J. I think we've all seen that before. If we look at Metropolis-Hastings, those are my transition probabilities. So you're computing them as you go. Kind of cool. So this is the transition probability. Let's think about the two-case example. I'll leave you with the concept. So here's just the two-state transition. So this is the probabilities of moving from I to J in one step. I want to leave you with this. You've learned this in the stochastics class. Any Markov class is probably week 1. A squared. What is it? Well, let's just look at it. Multiply A into A. It's these probabilities. Think about this. What does this say? This is saying in 2 steps, I can move from state 1 to state 1, and then move from state 1 to state 1 again. So this is staying in state 1 twice. Or what I could have done is I could have moved from state 1 to state 2, and then 2 to 1. So this is the probability of being in state 1 after 2 moves. This is the problem if I started in state 1. So starting in state 1, returning to state 1 in 2 loops. This is the probability of moving from state 1 to state 2 in 2 loops. So I could move from state 1 to 1, or 1 to 2 is what this says. This is not right. So you can see it. So this is this thing times that thing. So 1, 1 into 1, 2, and then 1, 2 into 2, 2. You have those together. So this is 1 moved to 2. This goes from 2 to 2. So this is starting in state 1, moving to 2. This is starting in state 1. This would be moving to state 1 right here, and then 1, 2. So this is 1, 1. Is what that's supposed to say. So this is the probability of moving to state 2, starting in state 1 in 2 steps. So A squared is the 2-step transition matrix. A to the n is the n-step transition matrix. So AN, the n-state, n-step transition. We're going to take this to the limit. And if it exists, we're going to talk about what that means. That's what a limiting distribution is. They don't always exist. There's 3 conditions. So over the weekend, maybe look these up, and we'll come back and we'll talk about these definitions. You need to understand this so you can build an efficient Markov algorithm. So you need to be able to tune your Metropolis-Hastings algorithm. What we're going to need, if we're going to be creating a limiting distribution, is we need that limiting distribution to exist in the first place. Knowing that G covers pi is enough, almost. So I need to tell you about this last condition on the sheet called A-Periodicity. So I need to make sure everything's actually random. The theory is a guiding light when you're tuning your algorithms. You want to know what they're supposed to do theoretically. So we're going to keep on this trajectory. We'll come back to my actual code, and then we'll talk about implementation. So we're kind of in the middle of this Markov thing that seems like it's tangential to everything else that we do in Bayes, but this is the whole premise for the algorithm that we use. So I think it's just as important as everything else. Keep in mind, your algorithms are just meant to sample from pi. It seems like all this work to sample from pi, but once we can do it, we can compute anything for i.e. we can forecast better than anybody else. Something like that. Okay, have a great weekend, you guys. And we'll keep on this conversation. I'll play around with the computer and show you what